Welcome back to ECE 340. Homework 1 is due in a week, not next time, and I think the reason I'm doing that is maybe next time I will do a little bit more MATLAB in terms of introduction type material, but I've provided some links to that on D2L, and I may need to give you another way of accessing that material if it's not really loading for you on D2L, but we'll You can get MATLAB for your home computer. You simply need to go to the site license of the U of A, and did I provide a link to that on D2L? I thought maybe I did, but maybe not. So if you go to site license on the U of A website, you can download the entire version of MATLAB to your machine. That's from the U of A's website. Pardon? You do not have to go to MATLAB directly. No, you won't want to go to MATLAB to try to find that. You'll want to get it from the U of A website. There's like a tutorial on the U of A website. Okay. You still have to go through MATLAB website to license it. It's all explained on the U of A website. And now how do you find that link? Just say MATLAB when the U of A, do a search. So try that and you should be able to find a way to access MATLAB. If you can't, you can always do it on the ECE machines. There are MATLABs installed there. So it's on the Oscar section. OSCR is what we're being told now. So now we're fine-tuning where our derivative is pointing us in the right direction, hopefully. And that's what we want to look at, actually, is how do we describe different systems and their characteristics. We'll do that after we talk about scaling and shifting the time axis, and combining those or taking those two into account at the same time is discussed briefly in section 1.2-4 of the textbook. And if we get that far, we'll talk about describing sinusoids via complex exponentials or Euler's formula. Let's start. Last time we finished with the one example where we were building things out of pi, or building a given given signal or waveform, building x of t from pi of t's. Where we were using pi of t to be this unit pulse. And now we want to create from that unit pulse, which we could write in terms of elementary functions, where the elementary function is the step input. That's just turning on the unit step at 0 and then subtracting another unit step that turns on at 1. And that will give us this pi of t. And what we were talking about when we finished last time was this waveform x of t. That was 1 for a while, and then at 2 it went up to 2, and then it was only 2 for 1 unit of time, and then it dropped down, and at 5 it completely turned off. I'm not sure my spacing is very accurate, but there's x of t. And somebody after class said, well, can't you model that? And you could model that as 3 pulses this way. Last time we stacked these up into Lego-like blocks. You could also think of having this first piece as a pi that's just stretched by 2, Then you add to that, well, basically that's now just a rectangular pulse. Then you add to that a pulse of amplitude 2 that's delayed by 2. Then you're done until you reach 3, and then at 3 you add in a pulse of width 2 that has an amplitude of 3/2. And that's another way of describing this x of t. But I actually want to talk about this to just allow you to get comfortable with the idea of shifting the time axis and scaling the time axis. And to do that, let's go ahead and reproduce this picture that we had last time. Here is, I think, what we were calling b of t. Then we had a c of t on top of that, and finally we had this other little piece that was the d of t. And let's now look at those in terms of the unit pulse waveform. Last time, I think we got all the way through it, but now I want to talk about it a little bit more in depth. From before, we said that b of t, how do we build b of t out of pi? B of t being this pulse of amplitude 1 going all the way of a width 5. How did we make that, or how did we describe that in terms of pi? Here we had to stretch the time axis, didn't we? Not compress it, but expand it. And to expand it then, we are actually dividing time in pi by the amount that we're trying to stretch or expand. In this case, we wanted to scale that by dividing time by 5 or multiplying time by 1/5. And that now allows us to scale the time axis for b of t. One way of thinking of that is you can just plug numbers in. And now, when you plug in t equal to 5 into the argument of pi, you now are getting the same, or now b of 5 is equal to pi of 1. So whatever pi was when its argument was 1 is now what b is at time t equal 5. And you can get a feel for, is this making sense, or is this looking like what I expected this new waveform to be? And we now have created this b of t out of pi. How do we model or describe c of t, which is this little piece right here? How is c of t, or is c of t, at all related to our unit pulse? Okay, we just need to delay it, don't we? We need to delay it by 2 units of time. That will give us then this amplitude of 1. We just take the normal waveform, pi of t, and as long as it's now delayed, so we now have a delay of pi of t by this value of 2, which allows us to re-express c of t as pi of t minus 2. If we plug that into the definition, it should give us the same result in terms of unit steps. If pi of t, again, is just u of t minus u of t minus 1, then c of t, which is pi of t minus 2. Now we're just saying replace everywhere there was a t in the pi of t formula, replace it with t minus 2. You now have u of t minus 2 minus u of t minus 2 minus 1, which says, oh, c of t, another way of writing that is a unit step turning on at 2, and then another unit step turning on at 3, but we're subtracting that second step from the first one. And that, again, is another way of expressing this little pulse that gets added on to the first b of t, and we're consistent. C of t is indeed pi of t minus 2. We've just sort of verified that by substitution. What about d of t? If we go back and try to find what b of t was, or d of t was this little brick. And these are just linear combinations of each other. And so now that we have b of t plus c of t, we want to add on d of t, but we would really like to express d of t in terms of pi as that new waveform. It might be helpful to just sketch that. In this case, our d of t is not too difficult to sketch, and we could very quickly write that as a linear combination of unit steps. We could say, oh, I'm just going to have a unit step that turns on at 3 with an amplitude of 1/2, and now I need to shut that off or turn it off at 5. And I can do that by simply subtracting 1/2 times a unit step that turns on at 5. So this is one way of writing d of t. Now what we want to do, though, is what about writing d of t in terms of pi of t? What are the adjustments to pi of t that need to be made? We need to scale the magnitude, don't we? So we need to scale the magnitude. That's the most direct adjustment, let's say. What else do we have to do? Pardon? We have to expand it, don't we? The pulse is just 1 width wide. We need something that's of 2 units in width. So we want to expand its time axis. By a factor of 2, and we know if we want to expand by a certain factor, that's dividing time by that factor. And right now, if we simply took these two adjustments to pi, do you see what that would give you on the time axis? What would these two steps produce in terms of a waveform? Pulse starting at 0 with an amplitude of 1/2, and then how long does it for 2 units of time? So that's not what we want for d of t. We want to then shift it 3 units, and that's then our last modification. We need to then delay it . Three units of time. Now, here's the big question for today. Does it matter which order we do these operations? So does it matter the order in which these operations or these three changes are performed. Now you have a 50-50 chance. Does it matter if I delay and then spread out, or if I spread out and then delay? I'm not sure you caught that, but as long as you do it right, it's okay to do them in any order, and that's a correct answer. But if you're just brute force applying this without really doing it correctly, the order does sort of matter. So I'm going to go ahead and say this is a qualified yes, just to make you aware that you need to pay attention to what you're doing. So let's just maybe do it in the reverse order that we identified them. Suppose we delay pi of t by 3. And I'm going to give that, I'm going to index this so that I can keep track of what I'm doing. I'm now saying, let me call that d sub 1. So the first operation I'm going to call d sub 1, and I'm saying that's pi of t minus 3. That's delaying pi by 3, which pictorially says that you can come out here to 3 and have a unit pulse of width 1. And that's now d sub 1 of t. And we could write that in terms of unit steps, either directly or indirectly by applying or delaying pi by t minus 3 from the definition of pi, or we can simply say that's u of t minus 3 minus u of t minus 4. Now, what if we expand the time axis? Now that we have delayed it by 3, what if we expand the time axis of, let's say, this intermediate piece or waveform d sub 1 of t by the factor that we said we needed to expand by, which was a factor of 2. Or I'm now saying, let's look at this, d sub 1 of t over 2. And I'm going to call that a new waveform. Let me call that d sub 2 of t. That's now d sub 1 of t over 2. But from our definition of d sub 1, I can replace t everywhere with t over 2, and I end up with u of t over 2 minus 3. If you just see up above on the top line now of the screen, I'm replacing t with t over 2. I'm expanding the time axis by 2 minus u of t minus 2 minus 4. And now what's that ugly mess? Well, if you look at this, how did I say you could get partial credit? 1 and 0, right? So that'll give you 1/4 of a point out of a 100-point problem. A lot of partial, nah, it might give you more than that. Maybe it'll give you 1/2 a point out of a 100-point problem. Maybe I'll be generous and give you 1 point. But you know this is either it's either on or off. Now you just have to determine when is it on and when is it off. Well, it's on when the argument is non-negative. So as soon as this argument becomes 0, that turns on, and it stays on as long as we stay positive, that argument. Well, that's going to happen then when t minus 2 minus 3 is greater than or equal to 0. And you could go on some scratch paper and say, okay, I have t over 2 minus 3 greater than or equal to 0. I can see that I can now add 3 to both sides. Okay, so this now boils down to t being greater than or equal to 6. Did I do the algebra correctly? So this is now t less than 6. So I turn on at 6 with this particular unit step and its argument. And if you did the same thing, you could find that u of t over 2 minus 4, that's the other piece that we were using to build up this d sub 2 of t waveform. This is 1 and 0. This is on when t minus 2 over 4 is greater than or equal to 0. And you can see that that is going to happen when t is bigger than 8. And so it's 0 for values of time less than 8. And now what does d sub 2 look like? D sub 2 doesn't kick on until way over here at 6, and then it turns on at 8, and we're still up at a magnitude of 1. And what do we have? We now have d sub 2 of t equaling d sub 1 of t over 2, which is really equal to pi of, what was d sub 1? D sub 1 was pi of t minus 3. So d sub 2, we just replaced t with t over 2, and d sub 2 now becomes pi of t over 2 minus 3. Is that what we need? No, that definitely is not but we shifted by 3 and we expanded by 2. It's what we were told to do. But we have to pay attention to how we do it, don't we? We have to do it correctly. So this is not what we need. And hopefully now you can see that maybe you need to be careful when you're combining these shifting and scaling operations to a waveform. That was the whole point of that exercise. What do we need? Let's do it another way. So now if we expand first before we shift. So let's expand time by a factor of 2. And I'm going to run out of subscripts. No, I won't. You guys have had discrete math. I can keep going on these subscripts, right? So this is d sub 3. D sub 3 of t, I'm saying, is now pi of t over 2. That now looks like a unit pulse, except now we've expanded the time axis by a factor of 2. And we could write d sub 3 many different ways. D sub 3 of t is pi of 1/2 t, which is u of 1/2 t minus u of 1/2 t minus 1. And what is this guy equivalent to? This u of 1/2 t, what does that look like? Or what's an easier way, or maybe a cleaner way to write that? U of 1/2 t, when is this u of 1/2 t going to turn on? At 0, isn't it? When does u of t turn on? At the same time. So we could actually just write this as u of t, couldn't we? This u of 1/2 t, expanding the time axis, doesn't mean anything, does it, for the unit step, as long as there's no time shift in the argument. So this u of 1/2 t, we could write as simply u of t. And doing the algebraic manipulation on the argument of u of 1/2 t minus 1, what does that look like equivalently? That's u of t minus 2. And that in red is exactly what we've pictured for d sub 3 of t. This is now another way you could write this is u of t minus 2. Well, you could even say, well, I don't quite understand that, but you could even say the following. You could say u of 1/2 t minus 2. And then if you bought this transition from 1/2 t to t, now you can forget the 1/2 in front of the t minus 2, and you can say, oh, that's just u of t minus 2. Is that making sense? That's now d sub 3. That's just one of the pieces, isn't it? Now we need to delay things. Let's now delay d sub 3 by 3 units of time. To delay, we just replace t with t minus 3 if we're delaying by 3. And this now becomes pi of 1/2, and we're replacing t with t minus 3, and that's now pi of 1/2 t minus 3. Or this is now pi of 1/2 t minus 3/2. But what was pi of t? Now we can replace the t's in the pi of t expression with 1/2 t minus 3 everywhere, and this now becomes u of 1/2 t minus 3/2 minus u of 1/2 t minus 3/2 minus 1. Or this is now u of 1/2 t minus 3/2 minus u of 1/2 t minus 5/2. And you can then do what we had done before. You can factor out the 1/2 if you want to. This is now u of t minus 3 minus u of t minus 5. And that's what we, whoops, I guess we never drew it, did we? But we now have, did I not label that? I guess I didn't. I could call that d sub 4. So d sub 4 of t now looks like that, and now we're getting closer to what we need, aren't we? This d sub 4, which I'm now saying is equal to d sub 3 of t minus, what did I say it was? D sub 3 of t minus 3. Now all we have to do is scale the amplitude. Or d of t is now 1/2 d sub 4 of t, but that was now 1/2 of pi of 1/2 t minus 3/2. Or you could say that's now 1/2 pi of 1/2 t minus 3 if you wanted to. And now we've written or expressed d in terms of pi's. And we're finished. Now we can say that x of t is actually made up of a linear combination of b, c, and d. Or, written in terms of pi's, that was pi of t over 5 plus pi of t minus 2. So we expanded, this was b, pi of t over 5. That's just stretching that unit pulse into a width of 5. Pi of t minus 2 gives us the same 1 unit width, but it delays it by 2 units of time. And finally, we just found d of t to be 1/2 pi of 1/2 t minus 3/2. If somebody wanted x in terms of pi's, now we have it. Questions on that? So you need to be careful when you're shifting and scaling the time axis. That's what I'm trying to drive home in this exercise. Just sort of put something down and look at it and say, is this what I want to have happen with a fairly basic waveform? And then you can check and say, this isn't what I wanted to do. I need to expand first or compress first and then shift in time. Is that clear? Enough shifting and scaling. Let's now get into systems. This is a class that is what? Signals and systems. So we need to cover both. Let's now talk about certain characteristics of systems. In particular, we want to be able to, given some description of a system, some model, we would like to be able to distinguish between a linear system and a nonlinear system. And we want to start analyzing later in the course with linear systems. They're much easier to deal with versus nonlinear. We also want to be able to identify time invariant versus time varying. Are my R's, L's, and C's constant with respect to time, or maybe the resistor changes with time, or age, or temperature? Maybe it's time varying. Maybe it's a capacitive microphone and your capacitance is actually varying with time. Is it time invariant or time varying? Is our system causal or not, or non-causal? Have you heard of causal and non-causal? What in the world is this non-causal business anyway? So let's see if I can just give you an example. So that was actually causal, okay? So that occurred after I made the announcement. If that would have rung before I started talking about causality, then it would have been non-causal. Does that make any sense? All right, so here it is. If a system produces the following waveform or response, let's say if a system produces the following output, from a unit step, and remember, what does a unit step? What's a unit step input going to look like? When does it begin? At 0. So I'm applying an input that starts at, I've drawn some time axis in the sand, and I said, okay, here's t equals 0, and that's what I'm gonna force my system with that input from t equals 0 onward with a magnitude of 1. Now, if the system produces an output that I'm going to show you in a little bit, then the system is non-causal. Here's the output that I am saying this particular system produces. I've now tapped this system at time t equals 0, but what I see is this, where the input was this unit step, u of t, which is 1 for t greater than or equal to 0 and 0 for t less than 0. So the input looks like this, and the output is anticipatory, isn't it? It starts before I even hit it. A lot of times I do a demonstration, but I've learned that that sometimes hurts. That's non-causal. Does that make any sense? I actually reacted before I even was hit. That's what non-causal means. Causal means if you hit something, then you get the result. You see the output after or at the same time as the input. This output anticipated this input, and it started responding at -2 when I haven't even hit it yet with a forcing waveform. This is now non-causal behavior. That's a non-causal system, and we want to be able to identify that. We also want to be able to talk about another system characteristic, which is instantaneous versus dynamic. To keep these sort of straight, you might just think of an instantaneous system as being an all-resistor circuit. If you have an all-resistor circuit and you apply an input, what happens to the currents or the voltages in that circuit? They instantly respond to that input, don't they? You now have an instantaneous voltage divider response or a current divider behavior with an all-resistor network. If you have a dynamic network, then you have a circuit that has energy storage devices. Things start building up or accumulating or holding on to this energy. So this is now a circuit with energy storage, or I might even say it has memory. And what circuit elements do we think of when I start saying, oh, we have energy storage going on in this circuit? L's and C's, right? Eli the Iceman. We have L's and C's. We have derivative actions. When you have derivatives in your equations, there's some memory. If you have integrals, that's building up information. That's now energy being stored. You have energy in your system, that's a dynamic system versus an all-resistor network. Now, what's an advantage of having a linear system? It's easy to analyze. That's the easy. Superposition holds. So now we can apply one signal and we can apply a completely different signal, and now if we had the linear combination of those two inputs, the output is just the linear combination of those two outputs that were produced by those individual inputs. So superposition holds, and that allows us much easier analysis capabilities. That's the advantage of a linear system. Let's now look at what that means in a more descriptive way. Suppose that I have a system and I'm going to apply x sub 1 of t as an input to that system. Associated with that input, x sub 1 of t, and that could just be a bump, it could be an exponentially decayed waveform, it could be a cosine, that produces now some output I'm going to call y sub 1. Now I get a different input, and I'm going to label that x sub 2 of t, and its associated output I'm going to call y sub 2. If I'm working with a linear system, then that is going to allow me to say something about a linear combination of inputs x1 and x2. So if I know how the system responds to x1, and I say that's y sub 1, and I also know how it responds to x2, and that's y sub 2, now I know how the system will respond when I give it a linear combination of x1 and x2. That's just going to produce an output equal to what? A1y1 plus A2y2. It's a linear system. This will now be A1y1 of t plus A sub 2 y sub 2 of t. Let's look at an example. Again, these are different characteristics of a system. Here is a linear system. Suppose that I have a system that is governed by the following differential equation. The input is x, and the output is y. And the output is governed by this combination of y and its derivative. And the input and the output satisfy this differential equation. What could you think of when you see this differential equation? Have we talked about this before? Pardon? It's going to be a decaying exponential, isn't it? That's one way of describing this. Do you see something else that we talked about on the first day? Pardon? What's the order of this system? It's first order, isn't it? So it's not going to have a real complicated behavior. If I injected a signal x, what's the output going to do? If I put in some x and now just imagine some waveform, what's y going to do? Pardon? I'm not sure I heard you. Did you say it will smooth it? It'll be similar. It's going to be a scaled version. The output is a linear combination of itself and its derivative. This is looking like a low-pass filter with a certain bandwidth. We'll get more comfortable with that, but you'll be thinking of this as a transfer function. Since this is a linear system, we could Laplace transform this and produce a transfer function. And that would be 1 over s plus 3. And that's a low-pass filter with a particular behavior. But let's look at it from these definitions that we talked about before. Why is this linear? Suppose that I now insert an input x sub 1 of t. Without solving anything, I'm just going to define the output to be y sub 1 of t. And if it's the output of that system, then it has to be governed by that governing differential equation. That's what results when I hit the system with a signal x sub 1. What if I hit the system with x sub 2? Well, then I'm just going to introduce another output, y sub 2. And now that's just by definition. I insert one waveform as an input, x sub 1. I'm just going to say that produces a y1 for an output, and that y must satisfy that differential equation. I inject or introduce a second input, and I'm just going to say the output associated with that, which has to satisfy that differential equation, I'm just going to call it y sub 2. Now, what happens if I consider a new input? And in particular, what if I make that new input a linear combination of what I already had? Let me just call this x bar of t. If my system is linear, then I should see what for the output? And now if you want to get cute, you could say y bar, right? You could just say y bar, and I would have to give you some credit for that. That was a cute answer. That was an appropriate answer. It's y bar. That's correct. If I put in x bar, then y bar is my output, but y bar needs to structurally look like the input. It's now should be a1 y1 plus a sub 2 y sub 2. That's what should happen if my system is linear. Let's see what happens. Let's just plug this set of relationships in. So I now have x bar of t. That's just a1 x1 plus a sub 2 x sub 2. But what was x1? x1 is equal to this left-hand side, isn't it? By definition. If that produces the output y1 and y1 satisfies this differential equation, then anywhere I see an x1, I can replace it with that relationship. I can now say this is equal to a sub 1 times dy1 of t dt plus 3y1 of t. And now I can do exactly the same thing for x sub 2. I can scale that by a sub 2, and by definition of y sub 2 and x sub 2, I have that result. Now let me just put things together. Let me factor out the derivative operation. Meaning, let me now say this is equal to something differentiated once. And that a1 and a2 are just fixed numbers. It can slide in and out of that derivative. So this is now an a1 y1 of t. That pulls off this piece. And it's also a plus a sub 2 y sub 2 of t. That pulls off this piece. Is that okay? But what is that in parentheses? This is just y bar of t. And let me do the other. I can now pull off the y1 and the y2. I'm going to pull out the 3 so that I now have that's plus a 3 times a1 y1 plus an a sub 2 y sub 2. And this is y bar of t. But that now says that I have d by dt y bar of t plus 3 y bar of t, and that's what I intended to show. That now is what I would have to do if somebody said, well, show that that's linear. Well, I can just say, let me put in one input, that produces an output, and it has to be governed by that differential equation. Give you a second input, it's governed by a second output, or it produces a second output that's related to or governed by that differential equation. This generalizes, meaning we can now have a general differential equation, and that is also linear. So a general differential equations, the way that I'm going to write those in just a minute, are also linear, meaning I can now go to much, much higher derivatives. I could say a sub 0, nth derivative of y of t with respect to t, plus a1, the n minus first derivative with respect to t, and so on, down to a sub n minus 1, dy dt plus a sub n y of t, equaling. And now I could have derivatives of the input. I could have b sub 0, d sub m, x of t, dt, or the nth derivative of x versus the nth derivative of y. Plus, and I could just keep going, the m minus 1 coefficient, dx dt, plus, whoops, b sub m, x of t. That's an nth order differential equation. N for Nevada, M for Michigan. If you can't hear my N's and M's, maybe you can distinguish between Nevada and Michigan. I don't know, what order was that system? Nevada. Oh, okay. How many zeros did it have? Michigan. Oh, M zeros. Sorry, just trying to break it up a little bit here. Let's now look or contrast that with something that's not linear. Here's something that's not linear. Y of t, dy of t dt, plus 3y of t is equal to x of t. This product causes the whole dynamic equation or dynamic system to be nonlinear. Just one product term can throw a monkey wrench into your linearity. So anytime one has a product of outputs, inputs, and or their derivatives, and I could even say integrals or antiderivatives, your system is nonlinear. That's just one way nonlinearities could be introduced, is by products. Here we have a product of the output and its first derivative. We could have just had y times y, or y squared. That would be a product, and that would be nonlinear. There are other nonlinearities. For example, if we had the sine operating on the output y, sine of y of t is a nonlinear term. And if that was now a part of your differential equation, your whole system would be nonlinear. Where this might be the output. All right, now let's see if the rubber hits the road, if we can make sense of this. Class participation. Whoa, that's too big for this screen. Well, we'll widen a little bit. Question and answer period. Is this system linear? This is checking to see if this warm classroom puts you to sleep or not. I had nothing to do with you sleeping, haha, right? It's the classroom, stifling. So is this, you know what we are, don't you? As human beings, what we can be represented by? A 100-watt light bulb. So if we have 40 students in here, that's like 40 100-watt light bulbs coming into this classroom. You know the AC has to be quite strong to overpower us, right? If we're all generating, if you had a 100-watt incandescent bulb, that's pretty hot, isn't it? Well, that's what we're doing. We're just sitting here emitting light. We're very bright, aren't we? We're ECE students. But we represent, if you wanted to model us, if somebody said, oh, go sit in this room, and I'm going to measure your thermal properties, it'd be like just putting a light bulb in that room on a socket, a 100-watt light bulb. So that's why you put us in a room, and we're not even doing anything, are we? Well, I am trying. You guys are not being that active. It's basically when you're at rest. If you're up and running around, it's more than 100 watts. That's why we can burn so many calories in a day's time. Where was that? Well, thermal systems can be linear also, okay? So we could model a system that's thermal and it could be linear. I think you told me that this was a linear system. So let me just go ahead and say this is a yes. It is linear. All right. Is this system linear? Now we're getting some feedback, aren't we, or some interesting responses. Is this system linear? How many people, well, I won't force you to, but I thought at one point I heard some yeses. We're trying to make sure that everybody's on the same page. What makes this nonlinear if indeed it's not linear? This product term, isn't it? It's kind of buried there, but we have y times y. That's a product term. We have y squared. Just this little piece causes that whole system to be nonlinear. If you tried to plug in x1 and here's y1, here's x2 and here's y2 solution, you won't be able to show that relationship that we showed for this differential equation. It won't happen because of this product of output. This is now this product term says that this system is not linear. So this whole system is nonlinear. What about this system? Is this system linear or nonlinear? Why are we saying it's nonlinear? We have cosine of the output. We could have had dy dt plus 3y equal cosine of x. Yes, sir.
I have a question about the nonlinear term.
Okay.
So if yt stays small, cosine of yt should just stay 1, right? But if that were something like sine of yt might be small.
So now, yes. So the question was, when, I think this is the question, when can we approximate a system that's nonlinear with a linear system? And that's what you will want to become familiar with, maybe not so much in this class, but in other classes. When could we linearize this system? So if you now have a nonlinear system, it's important to be able to linearize it if you want to model it. The comment was, what if this was dy dt plus 3 sine y equal x, and y was small? Sine of y is about y, isn't it? So if y stayed small, and small could be 30 degrees, maybe 20 degrees. It depends on what you want to consider. You could then maybe say, oh, well, this is behaving like dy dt plus 3y equal x when y is between plus and minus 30 degrees. And now you have a way of working with that differential equation. You've now approximated that nonlinear system. Right now, I'm just wanting you to get comfortable with, is this system linear or not? We will specialize with linear. Yes, sir. Yes, so you can expand this. The question or comment was, can you expand this cosine in a power series or in some series expansion and throw away the nonlinear terms? Yes. But what you may find is you might find that you have dy dt plus 3 equal x. That's actually not linear, because that 3 is just kind of hanging there. It's stuck. It just messes things up. You can't now show this a1x1 plus a2x2 producing an a1y1. So this is now our nonlinearity, this fact that we're doing a nonlinear operation on the output. Now this one, is this system linear? Maybe you can't, that's the system. Is this system linear or nonlinear? What do we think? I've heard some linears. Do we have any nonlinears? Why is this linear? It's got a cosine. But this cosine is not having an argument that's y or x or any of their derivatives. This is a cosine of the independent variable time. This is now a time-varying system. It has a time-varying coefficient. You could think of this as maybe an RC product, and the RC product now is a cosine of 6t. Oh, the RC is changing with time. Makes my job a little more challenging to analyze, but it's still a linear system. This is now a time-varying coefficient. But the system is still linear. Is that clear? This is what I get for doing this before class. So let me do this. Oh, I always get the wrong. Whoa, how in the world? Oh, well, we can do this. This is the final exam for 441. You're ready for that. Is this, whoa, I'm really ahead of things here, aren't I? So here is where I think I left off. Time invariant means fixed. If you had an RLC circuit, then your R's, L's, and C's are constant. They don't change with time. That's the difference between time varying and time invariant. The last system that we just looked at with the cosine of 6t, that had a coefficient that was a function of time. That was a time varying differential equation, but it was a linear differential equation. Causal. Remember what we said about causal? The present output depends on the present and or past inputs and not on any of the future inputs. And you could also call that a physical or non-anticipatory system if it's causal. This is a causal system. I inject an input X. It's a little bit fuzzy, but it's okay. It produces an output Y at the same time and the derivative of the output at the same time. Is this system causal or non-causal? How in the world do we even tell? Well, what I like to do is I like to just pick a specific value of t and see if I can relate my outputs, derivatives of outputs, and inputs to each other. And a time that might be convenient for this, suppose that I let t equal 2. Then I have y prime of 0 plus 3y of 2 is equal to x of 2. So at one instant of time, this relationship is true for this system. Does that tell us anything about this system's behavior relative to causal or not causal? Now I can see that the derivative of the output right now, if I called now 0, actually depends on an input 2 units in the future. This is x at time 2, and it's influencing the derivative at 0, meaning this is a future input, and it's influencing the present output's derivative. What does that mean? Causal or not causal? Here we are seeing that the output or its derivative, in this particular case, it's the derivative of the output, depends on future inputs. That means that this guy is non-causal. Yes, sir? Yes, so if this, I think this is what I hear you saying, if the right-hand side was x of 0 for this particular system or condition, yes, and y prime could have been of 2, then if x of 2, if y prime was 2, then this would have been just dy of t dt, and it would have been causal, because the present input would be adjusting or influencing the present output and its derivatives. Let's do another one. Is this system causal or non-causal? What's a convenient value of time to maybe play with? Maybe t equals 0. If I select t equals 0, I now have y prime of 2 plus 6y of 1 equaling x of 0. What does this tell me? Future outputs and their derivatives depend on the present input, don't they? So the present input is influencing future outputs. That's okay. I can kick this system and then it responds. That's basically what this is saying. I kick it at 0, and then in a second, that output and 2 seconds, its derivative, that combination will be influenced by that adjustment of the input. This is actually then a causal system. The outputs and their derivatives depend on previous inputs. What about this one? Causal or non-causal? Non-causal. What did you use for t? 0. I want everything to be positive. So I'm going to let t equal 1. I don't want to go negative and positive. So if I let t equal 1, I now have y prime of 2 plus 6y of 0 equaling x of 1. What in the world's going on here? My output at 0 depends on a future input at 1, doesn't it? So this is actually a non-causal system. What about instantaneous versus dynamic? What if I gave you the following set of equations? Y of t plus 3y squared of t plus cosine y of t is equal to x of t. Is that instantaneous or a dynamic system? Does this have memory? No. As soon as I pick an x, the output is determined, isn't it? It's at the same time. So this particular system is instantaneous and possesses no memory. Let's see if we can put all of this together, and you can tell me what we have. Now you can just start stringing all of these adjectives together. Suppose that I now have the third derivative of y with respect to t plus 3t squared dy of t dt plus 4y of t is equal to 6 dx dt plus 2x of t. What are some adjectives that describe this system? Is it linear or nonlinear? Did I hear both? Is it linear or nonlinear? Linear, isn't it? We don't have any product terms. We do have this t squared. Oh man, he's trying to trick me. But what is that t squared giving us? So this is linear. Is it causal? It's causal. Is it time invariant? No. Now we have a coefficient that has a t. It actually has a t squared, so it's time varying. Is it dynamic or instantaneous? It has some memory. It's dynamic. This third order linear, time varying differential equation and causal is now a way that we could, now you can go home and impress all of your friends. You can say, well, given a linear, causal, time varying, dynamic differential equation, that's where we will stop with today's lecture.